Hello everyone. In this lesson, we're going to be talking about a topic in chemistry that's a very popular topic in general chemistry called stoichiometry. Let's first talk about what is stoichiometry. Stoichiometry essentially is based on the principle of conservation of mass. That is to say that every balanced chemical reaction acts as a chemical recipe in which the proportions of reactants and products are specified. So when we balance a reaction, that is what we're doing. We are assigning the proportions that works at a molecular basis as well as the molar basis. Stoichiometry is the study of how a balanced reaction can be used to calculate the amount of an obtained product or a needed reactant given the amount of another product or reactant. So what do I mean by that? We can summarize a stoichiometry in this flowchart right here. So imagine A is the substance that's given. Now A represents either a reactant or a product in a chemical reaction. And B, let's say, is the one that we want to solve for, is the desired amount of reactant or product that we would like to solve for given A. Now, a few different ways that we can be given A. Number one, we can be given A in terms of the number of particles. All right, so that's a possibility. Another way we can be given A is the amount in grams of A. That's a more likely possibility. And if A happens to be a gas, we know that for an ideal gas at STP, we can use the volume. Maybe the volume of this gas is given to us. No matter how it's given to us, we want to first convert it to the moles of A. So let's say if it's the number of particles, we can use Avogadro's number, which is 6.022 times 10 to the 3 particles per mole, to convert it to the number of moles. If it's a volume of the gas at STP, by the way, STP stands for a standard temperature, which is 0 degrees Celsius, and a standard pressure, which is 1 atm. So if you want to convert from milliliter or liter of the gas at STP, you can use 22.4 liter for 1 mole of ideal gas at STP. Or if the mass of A, which is the most likely scenario, if A is not a gas, then most likely what we have is the mass of A in grams or milligrams, that we can use the molar mass from the periodic table to convert to moles of A. Once we have it in terms of moles of A, then we can use this mole bridge right here to convert it to moles of B. That mole bridge is the result of the balanced reaction. So we're going to go through an example next. So here's an example we're going to go through. Let's say we're given hydrogen plus oxygen. So this is what we will call a combination or a combustion also, because it's oxygen. This is exactly what happens in a hydrogen engine. The hydrogen are kept as in hydrogen fuel cells, and when they are combined with oxygen, they release power, and they release heat, and they produce H2O, or just regular water, at the tailpipe. So it's very environmentally friendly if the source of that hydrogen, where it's produced, where the fuel cells are produced, is environmentally friendly. So in this particular example here, we got half a liter of O2 at STP, and what we are asked is how many grams of H2O can be produced from half a liter of O2 at STP. The first thing that you notice we've done here is we balance this chemical reaction. So balancing the chemical reaction is as simple as keeping a tally, a good bookkeeping job on the number of elements on the left-hand side of the reaction and the right-hand side of the reaction. So we introduce these coefficients here that are going to be serving us when we use the mole to mole bridge in our stoichiometry. So these coefficients in the chemical reaction is what we're talking about with the mole bridge. They're going to tell us the mole to mole ratio that we have between the reactants and the products in a given chemical reaction. So the way we always start a stoichiometry problem is first we start with the given. So we were given half a liter, 0.5 liter of O2. So that's our starting point right there. And then we look at the flow chart. So we are starting here at the volume of a given gas at STP. So we use that conversion rate that we have for 22.4 liter of the gas for 1 mole of the gas. That's going to be the green giant one. So each of these basically conversions that we're making here, each of these fraction represents what we would call a giant one. What's in the numerator is equal to what's in the denominator. And we use this technique to do dimensional analysis and to do conversion, unit conversion, etc. So here, that's the first thing. So we have taken this from the liter of O2 to the mole of O2. Now we can use the mole bridge. So the balanced chemical reaction tells us 2 moles of H2O for 1 mole of O2. So that is this guy right here, the red giant one. That's the mole bridge that comes straight from the balanced chemical reaction. And lastly, we are being asked how many grams of H2O is produced. So we have the moles of H2O so far, but to convert it to gram, we're going to have to use the molar mass. So this is where we started in this problem, and this is what we want. So we are going down the path from the volume of the gas at A for A to the moles of A, using the mole bridge and the balanced chemical reaction to the moles of B, and from there to convert it using the molar mass from the periodic table. So 18.01 grams of H2O is the molar mass of H2O. In other words, 1 mole of H2O weighs on the scale 18.01 grams. So you can see here that all the units cancel, starting with the liter of O2. One is in the numerator, one is in the denominator. Moles of O2, they cancel. Moles of H2O, they cancel. And we end up with grams of H2O, which in this case, if I've done my calculation correctly, it turns out to be 0.804 grams of H2O. I hope you found this lesson helpful. I will be posting more lesson about the stoichiometry in the near future. Thanks, everyone.